Hello, am I audible? We will wait till 6:05 and then we will start the session. Hello all, it is 6:05 now, so I will start the session. So this is the live session of solid mechanics course on NPTEL. This is week 10. My name is Manoj Shikhar. I am one of the TAs in this course. I am a PMRFA scholar at IIT Delhi and I work with Professor Ajit Kumar in the Department of Applied Mechanics. I've done my BTech and MTech from IIT Kharagpur. And before starting the session, I'd like to declare one thing that though we are here to help you with your doubts and questions, please refrain from asking any questions which are part of currently active assignments on SOAM portal. We won't be able to help you with those. Apart from that, if you have any doubt, you can write in the chat or you can unmute yourself and you can speak. So in week 10, the topics which were covered are concept of shear center, theory of beams, mainly Euler-Bernoulli beams and Timoshenko beams were discussed, and the beam buckling was discussed. Now for the notes of this course and questions which are like competitive exams, you can visit this website. This is the website of Professor Ajit Kumar, and here you will be able to find all the PDFs of the videos which have been covered on the NPTEL portal. So we will slightly recapitulate what has been covered and then we will start our problem solving session. So in lecture 26, the concept of shear center has been discussed, and the main aim was to find the shear center of open structures. Okay. So because the to obtain the formula for the location of shear center for general cross section isn't feasible, so special cases have been discussed here. So in this we mainly find a point about which the net torque on the body will be zero if we apply a shear force. So that is the main concept of shear center. Now, suppose if we apply force on any point in the body, transverse force on any point on the body. So there it could result in the twisting of the body also. So to stop the twisting, we actually generally apply the force through the shear center. And as I told earlier, if we apply the force at the transverse force at the shear center, there will be no torque on the body. So twisting will not be there. Now to find the shear center for symmetrical cross sections, one thing to remember is that shear center will lie on the uh, axis of symmetry. Okay, so or lines of symmetry, not the axis of symmetry. So for example, here you can see in the big figure 3a, we have a ring. So a ring will have infinitely many axis lines of symmetry. So the shear center will lie on all of them. This essentially means that the shear center will be the point at which all these lines intersect, and that will be the center of the ring. Now in the second figure, you can see it is a heart-shaped cross section. So here we know that there is only one line of symmetry. So we will be able to fix only one coordinate of the shear center. That is, the shear center will lie on this line. And for the other coordinate, we will have to do the calculations. Now for the third case, we have a flower-shaped cross section, and it has four lines of symmetry. So the shear center will lie on each one of them. This means that the shear center will be the intersection of all these lines. So that will be the point of intersection of all these lines. So we will have a unique shear center point here. Without any calculations, we can say that where the shear center will lie. Now we will see this problem also. So I will leave it for now. Okay. So this was the concept of shear center. And after that, the theory of beams were discussed. So the beam is a slender body. It has two dimensions. So we cannot say any body as a beam. So uh, to level any body as a beam, it must follow these things. That it will have two dimensions which are very small compared to its third dimension. So if we want to geometrically characterize the beam, we will have to identify, or we will have to mention its length, and we will have to identify the type of cross section. So sometimes in books you will find that the beam is also characterized by its aspect ratio or slenderness ratio, and which is defined as the ratio of its length, that is L, this L divided by D. Okay, so this D is it may be a different quantity depending upon the cross section. For circular bar, depending upon the type of cross section, for circular bar, this D will be equal to the diameter of the circle. But in other cross sections, we may need to calculate what will be this D. Okay. So if the aspect ratio, that is L divided by D, is of the order 10 or higher, we say that it is a beam. Okay. And you can see that the body in figure 1A is not a beam since it does not have a well-defined length. It is something random is going on. Now, if you remember from the prior classes, we have read about the three-dimensional stress equilibrium equation. And to obtain the deformation of any body, we can use these equations. Okay. But if we use these equations, we also need to use the strain displacement relation and stress strain relation along with these three to completely find our solution. Now, this will be very expensive and many times it will happen that we won't be able to solve these by hands. And we may need to use numerical techniques or iteration or any other thing like FEM kind of tool to solve a problem. So, but in case of beam, since one of the dimensions is really big compared to others, it is assumed that if we can accurately find just the deformed center line and deformed orientation of beam's cross section, we would get an approximate deformed beam, and it has been shown here in the figure 2. And later on, sir has also shown that depending upon some aspect ratio, our assumptions will hold true. So the first theory is the Euler-Bernoulli beam theory. And here the assumption is that the normal to the plane, so the normal to the cross section, this is the cross section, will align with the tangent to the center line. Okay. So in Euler-Bernoulli beam, the center line and the normal, they will align with each other. So in the first figure, you can see the normal to the cross section. This cross section, it has this normal. This is not aligned with the tangent. If I draw a tangent here, so they are not aligned with each other. So this problem will be dealt in the next lecture in the Timoshenko beam theory. And in Euler beam theory, we assume that they both are same. So here, the orientation of the plane, the orientation of the cross section is not a variable anymore because we are assuming that the plane normal will be aligned in the direction of tangent to the center line. So the only variable we have here is what the direction of tangent to the center line. So center line is the only unknown here. And to get the required equation for it, we will use the bending formula we have read in previous classes, which was moment equal to EI K, where K was the bending curvature and EI is known as bending stiffness and M was bending moment. And we also know that the kappa, this K, sorry, not K, this was kappa. We also know that the kappa is the radius of is the bending curvature. So from mathematics, we know the formula of bending curvature. It is d2y dx square divided by 1 plus dy by dx square to the power 3 by 2. So we can replace kappa by this expression and we will find this expression. We'll find equation number 3 here. Now, if we look closely, we will be able to find that the above equation is actually non-linear in the unknown deflection y, and the horizontal coordinate x is also an unknown. In Euler-Bernoulli beam theory, the axial displacement is assumed to be negligible. This means that the initial and final x will be same. Okay, so the deformed axial coordinate x, small x, and the undeformed axial coordinate capital X, they are approximately the same. So we will be able to replace this small x in these expressions by capital X. So that is what they have done in equation number 5. And if we linearize the above expression in deflection y, we can also assume that dy by dx is very, very small compared to 1. So if dy by dx is very, very small compared to 1, its square will also be very, very small compared to 1. So we will be able to neglect this. For example, suppose if dy by dx is 0.01, so 0.01 square will be 10 to the power minus 4. So we can neglect this, and our equation number 3 will reduce to d2y dx square into ei equal to bending moment. And this expression is the expression of Euler-Bernoulli beam theory. And while deriving the Euler-Bernoulli beam theory, following assumptions have been uh, made. The first assumption was cross-section normal and center line tangent, they are aligned with each other. Axial displacement of beam is negligible, and the slope of beam center line is negligible compared to unity, where unity means 1. Okay. Now the problem which we had dealt till now, there we have considered that the center line tangent as well as the normal to the cross section at the same point, in the they are the same. They coincide with each other. But what if but that is not the case in most of the thick beams. So Euler-Bernoulli beam theory will be true for thin beams, and for thin beams, generally L by D ratio is greater than 20. Okay. For thick beams, like the beams which fall within the ratio L by D ratio of 10 to 20, for them we actually cannot apply Euler-Bernoulli beam theory, and for those cases we are forced to apply Timoshenko beam theory. And later on, we will be able to see that for a special case, the Timoshenko beam theory, it will reduce to Euler-Bernoulli beam theory. So this tells us that Timoshenko beam theory is a more general theory than Euler-Bernoulli beam theory. And here you can see we will be considering some angle between the normal to the cross section as well as and the tangent to the center line. So in the figure, it is assumed that the alpha is the angle between the tangent to the center line and the x-axis and the original x-axis, and theta is the angle between the x-axis and the normal to the plane. So we can see that these angles are not equal. Now, initially the angle between E1 and E2 axis was pi by 2. And if we find the angle between the cross-sectional line, so this E2 was the cross-sectional line earlier, and if we want to find the angle between the cross-sectional line and the center line tangent, then the angle will be this angle pi by 2 plus, because the angle between the normal and the plane will be pi by 2 plus this angle theta minus alpha. So pi by 2 plus theta minus alpha, and alpha is what? Dy by dx. Okay, so alpha is dy by dx. Earlier we had assumed this theta to be equal to dy by dx because theta and alpha were same. But from now on, remember that theta and alpha are two different things, and alpha is defined as dy by dx. So since there is a change in angle between two lines, there will be some shear strain between those two lines. So the total shear strain is what? Pi by 2 minus this change. So the value of shear strain is dy by dx minus theta. And the meaning of this superscript 0 here is that the shear strain is at the centroid of the cross section. Okay. So in Euler-Bernoulli beam theory, there is a correction factor K here. And for rectangular cross section, this value is 2 by 3, and it will vary depending upon what kind of cross section you are using. So in Euler-Bernoulli beam theory, we will have one expression dy by dx minus theta equal to v by kGa. And the other equation which comes from the moment curvature relation is ei kappa equal to moment. And in this case, we cannot write kappa as d2y by dx square. So here we do the change of variables. So we replace the length by r d theta, where d theta is the angle between the two cross sections. okay, which are very close to each other. So from there, we will replace dx. And so d theta by dx will become 1 by r, and that will be the radius of, so inverse of radius of curvature is the bending. So I'd like to show it from here. So this bending curvature, if you remember from the past classes, its definition was 1 by r. So that is what has been done here. We have calculated that, okay, what is the value of r? So d theta by dx was 1 by r. And that's why we'll replace this 1 by r using kappa. Okay. So the above equation of, and one thing to remember is that this relation will hold for Euler-Bernoulli beam also, because kappa is 1 by r. This is by definition. So our equation number 8 will transform into equation number 11, and we will have ei d theta dx equal to mx. Okay. So these were the two cross sections which I was talking about, and the relative rotation between those is d theta. So a small table here to, you should remember it. For Euler-Bernoulli beam theory, theta is equal to dy by dx, and d theta by dx is directly equal to del 2y by del x square. Okay. For Timoshenko beam theory, theta is not equal to dy by dx. Alpha is equal to dy by dx. Why? Because dy by dx is the slope of the center line. Okay. So this means that alpha, which is the angle of center line with respect to x-axis, that will be equal to dy by dx. In Euler-Bernoulli beam theory, both theta and alpha were same, so we were able to write this. So keep this in mind. And also d theta by dx will not be equal to del 2y by del x square in this case, as we have seen already. Okay. So when will our Euler-Bernoulli beam theory, and when should we use Euler-Bernoulli beam theory, and when should we use Timoshenko beam theory? So if so from this derivation, you can see that Euler-Bernoulli beam theory can be used safely if the beam is longer, or if L by D is greater than a particular cutoff value. For shorter beams having low aspect ratio, we have to use Timoshenko beam theory. Okay. So keep in mind that before applying EBT or TBT, you have to first calculate what is the slenderness ratio you are getting. And according to that, you will have to use your Euler-Bernoulli beam theory, okay? Or Timoshenko beam theory. Then buckling of beam was discussed here. Generally, we study the buckling of column. So in column, we apply axial compressive load. And what has been observed that even after applying axial compressive load, the column, it bends or it buckles. The exact term is it buckles. So for that, and for the buckling of columns or buckling of beams, the theory which we will use will be the Euler-Bernoulli beam theory. Okay. So what we do, we cut the section of this beam and we take the right hand side part. This part is at a location yx and this part is at a location yl, where yl is the displacement, the y displacement of the column at x equal to L. Okay. So if we do the moment balance about this point, we will get this equation. So from here we get the relation ei del 2y del x square plus py and pyl. So this is a ordinary differential equation, and the solution of this equation will give us the deflection of this column. Okay. So as from mathematics, we know that first we will have to find the solution of the homogeneous part. So in that case, we'll assume that RHS equal to 0, and then we will find the particular integral. So if we substitute y equal to e to the power lambda x, we will get this lambda equal to plus minus I, where I is the square root of -1, square root p upon ei. So from here, we have the homogeneous solution or the complementary function y equal to c1 cos root over p upon ei into x plus c2 sine root over p upon ei into x. And for the particular integral, if we substitute y equal to yl, we will see that our equation holds. This equation number 31 holds. So the total general solution of the non-homogeneous differential equation will become what we have written in equation number 35. Now in this expression, there are two unknowns, C1 and C2. So how do we find these unknowns? So to find these unknowns, we will need to find these unknowns, we will need to have two boundary conditions. And so for example, suppose if we have taken this example at x equal to 0, we have clamped the beam. So here the slope will be 0, and here the deflection, the y will be 0. So y 0 equal to 0 and theta 0 equal to 0. So if we do that, we will find that we have this expression for y. Okay. Now to obtain p, like, okay, we have found that this is the expression for y, but what will be the value of p, the critical value of p for which this beam will buckle? So we can use the fact that the above expression must be equal to yl if we substitute x equal to l. Okay, so if we write x equal to l, this will become yl. So yl equal to yl into 1 minus cos of this thing. So this means that cos of square root p upon ei into l will be equal to 0. And from here we get p equal to 2n plus 1 pi by 2 whole square ei upon l square. Now the critical value will be the value when small n is equal to 0. So that will be the smallest load, right? So in that case, if we substitute n equal to 0, we will get that p critical equal to pi square ei upon 4l square. So one thing to remember is that this expression of P critical, it will vary depending upon the boundary conditions. So on internet, you can find different charts where different boundary conditions with different critical loading will be available. You can also find those charts in many reference books. So this ends the discussion of buckling of the beam. And let's move on to solving some problems. So the question is, determine maybe I should show it from here only. So the question is question number 4, that think of a beam whose cross section has a shape of thin annular disk. So this is the cross section of a beam and it is thin annular disk. Annular disk means it will have two radius. So this is the inner radius and this is the outer radius. How will the shear stress distribution be in the cross section? Will such a beam undergo just bending or it can also twist? Okay, so this is the question. So this is basically a question for like you have to calculate the shear center. So you have to calculate the shear center of this beam, and then you have to say that, okay, if we apply the force at shear center, the beam will not twist. It will go just bending. It will undergo just bending. If we apply force at some other point, then there will be some effective torque in the beam, and then it will undergo twisting also. So how do we solve this problem? So the step one is like first we have to define the coordinate system. Okay. Question number 4. From tutorial 10. I will share the tutorial PDF also, so don't worry. So we have annular disk and the cut is very small. So we know from the discussion in the class that the shear center will be somewhere here outside this. Okay. So we have to find shear stress distribution. So we are assuming that capital R is the radius of the disk and this is the S coordinate. Okay. This is our Y axis, the vertical axis. And this is the delta Z. Okay, if you remember from the discussion of the symmetric cross section, so from there we know that the shear center will lie on the axis of symmetry. So we can directly say that delta y was 0 for this case. Okay. And this is our z-axis. So thus we know that the shear center will lie on this line, somewhere on this line. But from class we knew that this will lie outside, so I've shown it here. But you can start that, okay, it will lie on this line only, on the z-axis. Now the next step is we will consider a small cross section, okay, a small part of this cross section, d phi. So this is a arc we have considered. This is an arc we have considered. The This is this arc, the angle theta arc, okay. And suppose we consider this strip. This is our angle phi, and this is angle theta. Okay. And this angle is d phi. The angle subtended by strip is d phi. So what is the y coordinate here? This is r, and we know this is theta. So y coordinate, so z coordinate is r cos theta. Y coordinate will be what? R sin theta. Right? Now, similarly, this was for this arc. Now, for this small strip, for a small strip of subtending angle d phi, y is what? Y equal to r sin phi. Okay, this is the angle phi. So r sin phi, and z is r cos phi. So till now we have identified a tiny strip, which we have shown here by shaded region. It subtends an angle of d phi at the center, and the y coordinate of the center of this tiny tip is r sin phi. So the total area of this tiny strip will be what? Total area of this tiny strip, dA. This will be equal to r d theta, r into d phi, sorry, r into d phi into the thickness, r d phi into the thickness, right? So this will be equal to dr d phi, where t is the thickness of the frame or thickness of this beam we have taken. Now, small shear stress or the small shear force in this tiny strip will be what? So we will write it as dqy equal to y bar into dA. where y bar is the y coordinate of the center of this strip. So that will be equal to r sine phi. Okay, so this is actually y bar here. So the shear force in the but Q is not the shear force, it is the first moment of area. So y bar into dA, that will be r sine small dqy will be y bar into dA. This is r sine phi, y bar is r sine phi into the area was rt d phi. Okay, so from here we get r square t sine phi d phi. So if we integrate this dqy over the such tiny strips like the all the tiny strips, then we will get what? We will get qsy equal to integration of dqy from 0 to theta. And this will be equal to r square t into sine phi d phi from 0 to theta. So the integral of sine phi is minus cos phi. So minus cos phi from 0 to theta into r square t. And then we can replace this theta by. So how do we replace this theta? So you can see here r into theta will give us the s coordinate, right? The s length, the arc length. So I should write it here, r into theta equal to s. So from here we can replace theta equal to s by r. So we can replace r square t into 1 minus cos of s by r. Now we want, so why are we finding all this? So we actually want to find the shear center of this body. Okay, the location of shear center of this body. So that's why we have first found the QSY. Now we will find what is the IZZ. Okay, so now we shall find IZZ. Now here, see one thing. The cut is really thin. Okay? The cut is really thin. And the annulus is approximately complete. So while calculating IXX or IYY or IZZ, we can assume it to be a full ring. Okay, assume it to be a full ring and neglect the cut. So from here, what we will have is that IZZ equal to IYY equal to IXX by 2. This is from the perpendicular axis theorem, by the way. Suppose if this is the cross section and this is our y coordinate, this is our z coordinate, and x coordinate is somewhere out of the plane direction. So in that case, this will hold. So this will be equal to 1 by 2 into r square into 2 pi r t. You can find this from charts in the book. So this is equal to pi r cube t. Okay. So we have calculated IZZ also, and we have also calculated QSY. So the shear stress, okay. Shear stress when a transverse force of V is applied is equal to minus Vy QYS upon IZZT. Okay. So we will replace everything here. So this is the distribution of shear force, what they have asked us. Sorry, shear stress. And we know that for thin frames, the shear stress will be along the periphery, right? So for example, at s equal to 0, it will be minus Vy by pi RT. So this is the answer of part A, where we have to find the shear stress distribution. And if we want to know if the beam will bend only or if it will both bend or twist, in that case, we have to apply the shear force Vy from the shear center, and we have to calculate, okay, what will be the, so we have to calculate that, and if in that case we calculate the torque, it will be 0, because the definition of shear center is that the net torque about that point on the body is 0. So if we apply force from the shear center at the shear center, then the body will not twist. Then in that case, the beam will only bend. So in this case, if you calculate the shear center, you will find out that shear center lies outside the body. And if we want to apply the force here, okay, if we want to apply the force here, you will have to extend this body. So So to apply the force at shear center, we will have to create a thin extension on this body. This will be a thin extension. And here you will apply the load. Okay. So this is the shear center. Suppose this is our shear center. So here you'll apply Vy. Now to calculate shear center from this step, what you have to do, you have to use this formula. So you have to use this formula. Okay. And if you use this formula, you will be able to find what is this delta Z. Or in generic case, you will have to use this formula. So you can see here, after substituting this tau xs, we had gotten this formula here. So we can directly use this. And if you solve this expression, this integral, you will get what is needed. So hopefully this question is clear to all of you. Now we will move on to the next question. So there, the question is, think of a beam having a thin and open cross section. The shape of the cross section is shown in the figure. Suppose the beam is subjected to a transverse load at one of its end, such that force applied is along y direction, y-axis. Where should the load be applied in the cross-sectional plane at the tip so that the beam does not twist? Find out the shear stress distribution in the beam's cross-section, assuming the beam does not twist. Okay. So first of all, they don't want the beam to twist. That means that we have to find the shear center and we will have to apply the load at that shear center. Now they want us to find out the shear stress distribution in the beam's cross section, assuming that the beam will not twist. So, so, this is similar to the question what we have done earlier. So let's solve this problem also. So we know the expression of tau sx is minus qsy upon izzt. Okay. And when are these expressions acceptable? So if you look, so if we assume that the cross section y, if we assume that the force V is acting on the cross section and y comma z axis, they are also the principal axis. In that case, Iyz becomes 0 and our tau sx formula, it reduces to this Vy like tau sx equal to minus Vy Qis Izz Ts. Okay, so that is what we are using here. So while solving the problem, we need to take these things, we need to keep these things in mind that we cannot apply this formula everywhere. But they are under some assumptions that we are able to use these formulas. Okay, so our body was So from first look, we can see that this body has this line of symmetry. So the shear center will lie on this line. Line because this line is the line of symmetry. Okay. So, and also they have given in the question that the thickness T is much smaller than this length A. Okay. So assume that thickness T is much smaller than A. So this is what they have given. Now, since this frame is thin or this beam is thin, we know that the shear stress will lie along the cross section's periphery. We know this, right? So this will be how the shear stress will be there. Now we know this expression. So in each of these, let us write it as 1, 2, 3 possibly. Maybe so the top one is 1, this is 2, and this is 3. So we have to find tau sx in each of these. So tau sx in the first part, okay. This is V times V is the shear force we are transverse force we are applying. A plus T by 2 into ST. For this, S will be in this direction. Okay. For the second part, S is something like this. Divided by IZZ T. So this will be equal to, since T is very small compared to A, this will be equal to V into A into S upon 2 IZZ. Okay. Okay, from where this A plus T by 2 came? This came because if you calculate this QYS, okay, this will be equal to Y bar into area. Area is S into T. Area is S into T. And what is the Y bar? The centroid of this portion, the centroid. So suppose we have taken a small portion out of it. Suppose this is our small portion. So this is our small portion. Its length is S and its thickness is T. So where is the centroid located? Suppose this is the centroid. And this was our 0, 0 point, right? This was our 0, 0 point, 0, 0 point. So first we have to go A by 2. So this length is A by 2. And this length is, this is T by 2. So the total length will be what? So this will whole be A plus T by 2. This is our Y bar. So QSY will be what? A plus T by 2 A plus T by 2 into ST. And that is what has been written here. Okay, so that is what has been written here. Thus, our tau Sx for the first portion is VAS by 2IZZ, and we are assuming, and since it is given that T is much smaller than A, so we have approximated A plus T by 2 by A. For the third part, this is our S direction. And if we solve this, for third part, our tau Sx will be VQ upon IZZT. Okay, so V upon IZZ. What will be Q here? Q will be Y bar into A, but this time the Y bar will be for the lower portion, and lower portion is where it is at minus of A plus T by 2. Okay, into ST. So for third portion, tau Sxx will be minus VQ. So this T will cancel with this T, and this A plus T by 2 will again be approximated as A. So this will be minus VA by 2IZZ. Here it was VAS. Okay. VAS by 2IZZ. Here it will be minus VAS by 2IZZ. And for the second part, tau Sx will be so here the trick. I will write it the final answer, but I will show you the trick here. So how do you find Y bar here? Or how will you find the area here? Okay. So suppose this is your area. So the S we have taken is like this. So suppose if at a particular S, suppose if our S is somewhere here. Uh, Suppose this is the point where we are taking S. So the cross section above that is this is the neutral axis, by the way. I forgot to mention it. This is the neutral axis. So here we have S. This is our A by 2. This is the thickness. So we have, and this is the thickness. So here we have to calculate the Q for this complete part. Okay. So how will we do this? We can assume this to be one of the rectangles, and we can assume this to be another rectangle. This is another rectangle, and this is another rectangle. The thing is that we have been given that small t is very small compared to a, so there will be some approximations. Okay, so let's find what will be VQ upon IZZ into T. So what will be Q for second case? So Q for second case will be what? Y bar, and let's write this as A1, this as A2. So Y bar 1 into A1 plus Y bar 2 into A2. So we know that Y bar 2 is what? This is A plus T by 2. This is equal to A by 2. Why? Because we have assumed, or we have been given that A is very large compared to T. What will be Y1 bar? Y1 bar will be A minus S upon 2. Oh, sorry. A by 2 minus S upon plus S. So the centroid. So suppose if we had this is our A1. The thickness of this A1 is what? This is A by 2 minus S. Okay. So A by 2 minus S is the total thickness or the total height of this A1. So its centroid will lie at A by 2 minus S by 2. But what will be the coordinate of that centroid? Our axis is our coordinate axis. They are starting from here. So we need to add plus S here. So the coordinate of this point will be, this will be S plus A by 2 minus S upon 2. And that is what has been written here. Now, we also know what will be A2. A2 is this A minus T. But since or this is complete A into T. Okay. So Y2 bar into A2 is A by 2 into AT. Similarly here, A1 is what? The total thickness is A by 2 minus S. The total height is A by 2 minus S into thickness into T. So Y1 bar A1 will be S plus A by 2 minus S upon 2 into A by 2 minus S into T. So from here we can write Q equal to A by 2 into AT plus S plus A by 2 upon 2 into A by 2 minus S into T. So we can simplify it as A square T upon 2 plus A square upon 4 minus S square into T by 2. So this is our tau sx. So tau sx will be, so for the second part, tau sx will be V upon Q upon Izz into T. So this will be V upon V into 5a square upon 4 minus s square, or we can write it as, because T is gonna cancel now, 5a square upon 8 minus s square upon 2 into T upon Izz T. So this will be V by Izz into 5a square minus s square. Now, what is the Izz? So Izz is like total second moment of area for beam. So Izz is what? Izz1. Let us write this point as O. Suppose this origin point was denoted by O. So we need to calculate Izz about that point. So because that is the point on neutral axis. So Izz1 to so if we look closely, we will understand that Izz1 and Izz3 will be equal, and they will be calculated using parallel axis theorem. So 2 times Izz1 about O plus Izz2 about O. Okay. So Izz2 is what? This is 1 by 12 AT cube or A cube T. So one by 12. This is our 1, right? This is 1 and this is our 2. This is 2. So in this case, suppose this is Z axis. Oh, no, they are given Z in the opposite direction. So this is our Z axis and this is our Y axis. This is T. Here we have local Z, suppose Z1, and this is Y1. So 1 by 12 into A into T cube plus this difference. Okay, suppose if this was the centroid, so what will be this D? 80 into D square plus 1 by 12 into here our height is A and the base is T. So T into A cube. So this is Izz2, this is Izz1. Okay. So again, total Izz will be, so D is what? D is the centroid of this one. D equal to centroid of area 1. Area 1 equal to a plus t by 2. This is same as a by 2. Okay. So our izz will be 2 times 1 by 12 into 80 cube plus 80 into a square by 4, a by 2 square plus 1 by 12 t into a cube. So izz is 1 by 6 80 cube plus 1 by 2 a cube t plus 1 by 12 a cube t. So this will be 80 cube upon 6 plus 7 a cube t upon 12. So if we replace this izz here, here, and here, we will get the value, the distribution of tau sx. Okay, so this is the second part. And to obtain the shear center, we have to find the total torque. Okay, so the total torque is what? So replace these izz in the expressions of tau xy, expressions of tau xy to find distribution tau xy corresponding to 1, 2, and 3 to find distribution of shear stress, stresses in 1, 2, and 3. Respectively. Now to find the shear center, to find the shear center, we calculate total torque about the origin. We calculate total torque about the origin. So again, let me draw the figure here. So this is the origin here. This is our first part. This is our second part, and this is our third part. And we know that shear stress distribution will be something along the periphery. So it will be something like this. So that total torque will be what? Total torque should be, this is origin. So the total torque T will be what? Torque due to part 1. So 1 torque in part 2 plus torque in part 3. Now what are the things we know? We know that the direction of shear stress here and here will be opposite because it should flow. So suppose if this is in this direction and we are looking from this origin, so our small r vector is like this. So if you do the cross product r cross f, so this will be something. So suppose if outer direction is the ith, the direction of x, it will be I hat. Okay. Now if we look at the bottom point Here the R vector is what? So R top. Here R bottom. But here the direction of shear stress is this. Here the direction was like this. So essentially we will get the torque in the top part and in the bottom part in the same direction. If you do the cross product again, this is your radius R and this is your force. If you put it like this and if you do the cross product, you will see that it will be going out of the plane again. So it is I hat again, and also the magnitude will be same. So we can write it as T equal to 2 times torque in one. Maybe I should write it as torque in one, torque in two, and torque in three. Okay. And one more thing, the shear stress distribution in the second part, it is passing through the origin. So the total torque in T2 will be what? It will be 0. So this is 0. So our torque becomes 2 times T1, whatever it will be in this part. So we know the shear stress distribution. So we will replace that. The limit of S is what? Suppose this is the direction of S. So S will start from 0 to A. Okay. It's upon 2 IZZ. Okay, and the area. Okay. So this is what I missed. So this is our tau xy. Remember this formula. So we have to replace here. Now we will replace the value of IZZ. Now we know that we will have to apply the shear force V at shear center E, and that will should be equal to our torque. So V into E equal to T, and we will replace T by VA cube upon 4 T square by 6 plus 7 upon 12 A square. And from here we will get E equal to A cube upon 4 into T square upon 6 plus 7 upon 12 A square. And this distance is along Z axis, okay? Along Z axis. Anyways, so I will take a short break here. And after that, after 5 minutes, let's meet again and we will solve the problems further. Hello all. So for this question, while calculating the torque, I'd like to mention one thing that why did I write 80 by 2 here? So this 80 by 2, you may confuse it with area. Okay, but this is not the right thing. It should be A by 2 into TDS. Okay, so I will explain this here. What does this mean? So let's start on a fresh page. So this was the portion which we are considering, right? We are calculating torque on this portion, right? Now, this was our s-axis, and this thing is, and we are writing torque about origin. So this thing is a plus t by 2 distance away from the origin. We know that the torque is the torque is generated because of this shear stress distribution available here, and the thickness of this beam is t. So suppose if we take a strip of thickness ds, so this is our strip ds. So what do we know at ds? The width of strip is ds, the thickness is t, and some tau s is sx at s. Okay, so at some length s, at some distance s, we are taking a strip ds. Listen to what I'm saying. This ds, a strip of thickness small ds, is taken at a distance s from this corner. So we write tau sx d at that s, and the thickness of this trace is ds. The thickness of this strip is ds. The sorry, the width of this strip is ds and the thickness is t. So the total force will be what? Df equal to tau sx at s into T into ds, right? So this is the area. TDS is the area of this strip. The strip. So what will be the torque? Torque on that strip? Torque on a strip? This will be equal to, suppose this is the R vector. R vector cross this DF vector. So in this case, DF was in the K hat direction. Okay. And R is in Y hat direction. I should follow the same convention. So this torque is what? Dt equal to, for R, I will replace by A plus T by 2 J hat cross this df is tau sx at s into TDS into K hat. So J cross K gives me I, and also we are assuming this to be equal to A by 2. So our dt became A by 2 into T into tau sx at s into ds into I hat. So if I want to find the total torque, to find total torque, I will have to integrate total torque on reason 1. So this was our reason 1, right? So S will go from where? 0. Here S equal to 0, here S equal to A. So we need to integrate dt from S equal to 0 to A. And that is what has been done there. So basically our T is dt integrated over 0 to A. So this was what? 0 to a by 2 into t into tau sx at s into ds. And the direction is I hat out of the plane, which we also saw while doing the cross product. And then we replaced the expression of tau sx. So in the next step, replaced the expression of tau sx for reason 1 for reason 1. And this was equal to what? V into A into S upon 2I ZZ. And that is how we calculated the total torque. So I hope this is clear that why this A by 2 came here. Okay. I thought that I should show you the way, because it may have created confusion in some of you that a by 2 into t, is it some area or something like that. So now you know why a by 2 is there. So now we will be able to do, I think, one more problem and then we will end this session. So let's do this problem, the question number 2. I hope I have turned on my mic and camera. Yeah. Suppose a beam is kept with a roller support at one end. So this part has been done by sir in the class. So I'm leaving this question. I'm going for the second question. Suppose a beam is kept with roller at one end at x equal to 0, constrained to only move in y direction. So this beam B can move only in the y direction. It cannot move in x direction. Okay. And pinned at the other end at x equal to L. So at x equal to L, it is pinned. Beam is subjected to transverse load P at the middle of the beam. So they have applied the transverse load here. Find the deflection of beam using Euler-Bernoulli theory. So question 2, tutorial 11. So they have given us a beam. It is pinned at x equal to L, and there is roller support at x equal to 0. So this is our x-axis. And this is our y-axis, right? And at L by 2, our load P is applied. Now, at what point they want us to find the deflection? So find deflection of the beam using Euler-Bernoulli theory. Find deflection of beam using BT. Okay. So if you look at this problem, so the constraint at the left, it is frictionless. It has frictionless roller. So this allows us free translation in the vertical direction. Like in y direction, it can move freely, but it does not allow the beam to rotate. So there is a reaction moment at the left, but there will be no vertical reaction force. So the beam, as given in the question, the beam can move in the y direction, but it cannot rotate. So if it cannot rotate, this means that there is some reaction moment. So the reaction moment is present at x equal to 0. That is capital M at x equal to 0 will be some value, but the shear force will be 0. The reaction force in the y direction will be 0. And now in the question, they have given that the right end is sitting on a pin joint, which allows us for free rotation. So at pin joint, the free rotation is allowed, but it will not allow translation. So at this end, the reaction moment will be 0, but the vertical force will not be 0. So at x equal to 0, moment is not 0, but reaction force is 0. At x equal to uh, at x equal to L, moment equal to 0, but the reaction force will not be 0. So let's write the points here. So this is our point A and this is our point B. So let's first make the free body diagram. So B is basically at x equal to L, A is at x equal to 0. And here we will have MA. And there is one force P. And this P acts at L by 2. So first we do the force balance in the y direction. So P plus RB equal to 0. This means RB is minus P. Okay. Then we will do the moment balance. So moment balance, I'm assuming that counterclockwise is positive. Okay. So let us write moment about point A. So summation of moment about point A. So minus MA because this is in clockwise direction. Minus MA plus P into L by 2 plus RB into L equal to 0. This gives me minus MA plus PL by 2. RB is minus P into L equal to 0. So we have MA equal to minus PL by 2. So we have found the moment MA and RB. Now this negative sign, you may have read this in your statics class also. So this negative sign means that we have taken the wrong direction of RB. So in reality, RB is acting downwards. Similarly, in reality, the moment MA is acting counterclockwise. That's why it is coming with a negative sign. So we have taken a direction different from what it actually is. That's why it is coming with a negative sign. Suppose if we had taken RB in the downward direction, then we had gotten RB equal to plus P. I hope you know these things. So anyways, I will move on to the solution. Now we are considering that the origin of the system is here. So this is our origin on the left hand side. And in the question, they have given us that of so basically origin is at point A, which I have also written here. They are telling us to use Euler-Bernoulli beam theory to find the deflection. So what is the EBT? EBT is EI del 2 y upon del x square equal to moment, right? So this is our Euler-Bernoulli beam theory. So to use this formula, we will have to find the expression of mx. And first you should understand, I think if you have done the statics course or the mechanics course in first year, in my college, actually in first year, we used to first read statics. And after that, we used to uh, read some like solid mechanics part. And in that we read SFD, BMD. So from there, you may be remembering that if there is some point load acting here in between this beam, then the expression for moment will be different in this region. So if I do some partition here at L by 2, here we will have some different moment and here we will have some different expression for moment. Okay, so we will have to consider two cases separately. So to use above equation, we need mx, expression of ms. Mx in beam. Also, mx will have different expressions for x equal is less than equal to L by 2 and for x is greater than equal to L by 2. Because there is a point load in between, because there is a point load P at x equal to L by 2. So we have to keep these two things in mind. So let's find the expression for mx for x is greater than L by 2, for x greater than equal to L by 2. So here we have ma. This is our x. Okay, and here our force P is acting, right? So we are considering, so we will take what? We will make one section here. And we will consider the right part of this section. So here RB is acting. So we will draw this section here. Now on this face, the normal is in minus x direction, that is minus I hat. So the moment and shear will be, and so the moment and the shear force will be in that direction only, in the negative direction. So this is our Vx and Mx. Okay. Summation of Fy equal to 0 will give us RB minus Vx equal to 0. So from here we will have RB equal to Vx, or Vx equal to RB. So Vx equal to minus P. Now summation of moment equal to 0. Okay. So we are taking moment about. Okay, let's mark this point like maybe Q, not Q. Let this point be D. Okay. So here it is D. So moment about D is 0. Since shear force is passing through the same point D, it will be have no moment about that point. So we have minus mx plus rb into L minus x. That is equal to 0. So from here we have mx equal to minus rb into L minus x. That is p into L minus x. Oh, I missed a minus sign. That's why it was coming wrong. So mx equal to minus p into L minus x. Now for x less than equal to L by 2. So we are cutting a section here. Let this point be F. And we are taking this part. Okay. So again, let's draw our part here. So I tell you, so this is our P, this is our RB. Okay. The whole length is L minus X. So on left hand side, the normal is in the negative X direction. So our moment and shear force will be in the negative X direction also. So this is mx. This is Vx. And the whole length is L minus X. This is L minus X. So again, we will do the force balance. So summation of force in y direction equal to 0. So this means Vx minus Vx plus P plus RB equal to 0. We know that RB equal to minus P. So minus Vx plus P minus P equal to 0 implies that Vx equal to 0. So shear force is 0 in the left hand side part of the beam. That is when x is less than equal to L by 2. And the moment expression will be summation of m about f is 0. This point is f, or should I write it G? Because I'm using f for something. Let this point be h. So moment about h is 0. So minus mx plus this distance will be L by 2 minus x. Okay. So minus mx into L by 2 minus x into P. I'm assuming this to be positive into P plus RB into L minus x equal to 0. So from here we have mx equal to P L by 2 minus x minus this RB is replaced by minus P into L minus x equal to. So expression of mx is PL by 2 minus PX. I'll write it like P into L by 2 minus X minus L plus X. So this is minus PL by 2. And if you think carefully, this is what it should come also, because you see our shear force is 0. And if you remember, shear force is what? Differentiation of this moment with respect to x. So if differentiation of this expression is 0, this means that m should be constant in that part. So if in that part at some point we have found m equal to minus PL by 2, it should be the same. And that is what we are getting here also. Now we know that to solve the Euler-Bernoulli beam equation, this equation, we need boundary conditions, right? So what are the boundary conditions? So boundary conditions are for this problem are so first boundary condition is for x less than L by 2. Okay. This boundary condition is for x less than L by 2. Slope at x equal to 0 is 0. This means dy by dx at 0 is equal to 0. And the reason behind this is that we have moment not equal to 0 at that point. Okay. So we know that if the moment is not equal to 0, this means that our slope should be 0 at that point. Now our boundary condition 2 is for x greater than L by 2 at x equal to L, displacement is 0, right? Displacement is 0. This means y equal to 0 at x equal to L. So let's find expressions for yx separately for x less than equal to 0. Sorry, x less than equal to L by 2 and x greater than equal to L by 2. Okay, so for case not equal to, it should be less than here because we cannot write equal to at both the places. For case x less than L by 2. Okay. So what we will do, we will use EI d2yx dx square equal to moment mx for x less than L by 2. So what should this be? This will be EI del 2y by del x square equal to minus PL by 2. So on first integration, it will be EI dy by dx equal to minus PL by 2x plus C1. So using BC1, dy by dx at x equal to 0 implies that EI into 0 equal to minus 0 plus C1. So from here we have C1 equal to 0. So our expression reduces to EI dy by dx equal to minus PL by 2x. So again integrating. With respect to x, this was we found on integrating with. So from here we have integrated once we found this expression. Now we are again integrating this with respect to x, and we will find EI into yx equal to minus PL by 2. Or I should write it as. So we can write this as dy upon dx equal to minus PL upon 2 EI x, right? So if we again integrate this, so we will get what? We will get yx equal to minus PL by 4 EI into x square plus C2. So this is the expression for x less than L by 2. Now we have to find for x greater than L by 2. Mx is what? Minus P into L minus x, right? So EI del 2y del x square equal to minus P into L minus x. So on integrating once we get EI into del y by del x equal to minus PLX minus Px square by 2 plus Px square by 2 plus some constant d1. Then again integrating we will get yx equal to minus PLX upon EI plus Px cube 6 EI plus d1x upon EI plus d2. This is the expression of yx. Now at x equal to L by 2, we can use the continuities of slope of y. So dy by dx at x equal to L by 2 minus, this means that just before L by 2 should be equal to dy by dx at x equal to L by 2 plus. Okay. So if you solve this, you will get PL square upon 4 equal to minus PL square upon 2 plus PL square upon 8 plus D1. So from here you will get D1 equal to PL square upon 8. So we can substitute the value of D1 here, and then we will use boundary condition 2. So our new expression for Yx is 1 upon EI into minus PLX square upon 2 plus PX cube upon 6 plus PL square X upon 8 plus D2. Using BC2, at X equal to L, Y L equal to 0. So this is the our boundary condition. So from here, 0 equal to 1 by EI into minus PL cube upon 2 plus PL cube upon 6 plus PL cube upon 8 plus D2 equal to 0. So from here we get D2 equal to 5 PL cube upon 24. Okay, so you see we have found D1, D2, and we have found C1, but we still have an unknown C2 here. Now the conditions which we have used are that for x is less than for x less than L by 2, our slope was 0 for at x equal to 0. For x greater than L by 2, our displacement was 0 at x equal to L. And similarly, we have also utilized that at x equal to L by 2, the continuity of slope of y was there. So the last thing which we can use is that at x equal to L by 2, using the continuity of displacement. Okay. Of displacement. So y from L by 2 minus should be equal to y from L by 2 plus. Okay. So substituting everything, you will get C2 equal to 11 PL cube upon 48 EI. Do this exercise by yourself. Okay. So this is what you will get. So fine, I'll write the final answer now. So our expression for yx is what? So this is minus PLX square upon 4EI plus 11 PL cube upon 48 EI. This is for x less than L by 2. And this expression is 1 by EI into minus PL x square upon 2 plus px cube upon 6 plus pl square x upon 8 plus 5 pl cube upon 24 for x greater than equal to L by 2. Okay. So I hope this question was clear to all of you. Now, since it's already 8:16 now, so I'd like to end this session. If any one of you have any doubt, you can ask me right now, or I will end this session. You can write in the chat, you can unmute yourself and speak. So, okay. So since none of you have any doubt, I will end this session. Thank you for joining. I will meet you again for week 11 in next week on Tuesday from 6 to 8. I am Manoj Shikhar and I'm from IIT Delhi. I'm a PMRF scholar here. Thanks a lot, all of you. Goodbye. Have a nice day.